Assalamualaikum and a very good evening, everyone. Today we're going to continue with our lecture. We're going to look at chapter 9 as a continuation for our lecture. In this chapter, we're going to look at memory interfacing with the 68K microprocessor. So the objective of this chapter is for you to identify the types of memory chip and their functions. Secondly, for you to define the difference between full and partial address decoder. And lastly, for you to design the address decoder using full and partial technique. But for today, I'm going to split this chapter into two, and I'm going to cover up to design the address decoder using a full technique. We're going to look at on how to design using partial technique in the next section of this chapter. Okay, for today, first we're going to look at the types of memory available in a computer system. So I think all of you have familiarized yourself with the types of memory that is available in a computer system. We have ROM and then we have RAM, so this no need to be covered again. We're going to look at first what is read-only memory. Okay, so basically in a computer you have two types of memory. You have your RAM, which is your random access memory, and then you have your ROM, which is a read-only memory. So read-only memory is a type of memory that is permanent or semi-permanent data storage system. It is non-volatile, meaning that even after you turn off the power supply, the contents of this read-only memory will remain. And it's used to store the program, and there's a lot of types of ROM available in market. So the way you can imagine what ROM is for you to imagine your SSD. SSD is a type of ROM actually. A flash drive is a type of ROM, but not your hard disk drive. HDD is different than ROM. Okay, so I'm not going to go into detail about what's the difference between HDD and ROM, but HDD is something like you can store permanently, but it is not ROM. So that is for you to research by yourself. So we have what we call as a read-only memory. This is programmed by the manufacturer of the read-only memory, manufacturer chip. This can't be reprogrammed. And then we have what we call as a programmable ROM. It can only be programmed once using PROM programmer. Okay. And then we have what we call as a EEPROM. It can be programmed using a PROM programmer, but if you want to reprogram it, you have to use what we call as a COAS window, in which you need to use a UV light to erase the content of the PROM. Okay. And lastly, we have what we call as a EEPROM, electrical erasable programmable memory. This can be programmed using PROM programmer, and you can overwrite your previous program inside this memory. So this is the types of read-only memory that is available in the market. Okay. So, but actually, this part of memory, it can be considered old type of memory. We don't use this anymore. But EEPROM, you can still find a lot of microcontroller, for example, Arduino, for example. You can still find Arduino still using this EEPROM. Okay. Nowadays, I don't think there is EEPROM or PROM or ROM, but EEPROM is still here. Okay. So widely used here. Still widely used. Okay, then we're going to look at what is the typical diagram of your ROM system. Okay, this is a typical diagram of a ROM module, okay, EEPROM module. You have a connection to the address bus. You have connection going to the data bus. Okay, all of these buses is going to be interfacing with your 68K. Okay, you have your 68K chip over here. The address bus and the data bus will be connected to this EEPROM module over here. And then you have other type of pin. You have OE, which is output enable pin. We have CS pin, which stands for chip select pin. And then we have this VPP, the programming voltage, used by EEPROM programmer to change the bit value in the chip. And ground in your 5 volt is pretty much straightforward. So this pin over here, okay, this OECS pin here is used according to this description. Okay, so depending on the state of the pin, you can select either of this mode for the EEPROM. For example, if it is 10, you will deactivate the pin, use minimum power. If CS is 0 and OE is 0, it means that the EEPROM is in the right cycle and the data in this EEPROM are put onto the data bus. If it's in 01, it is in standby cycle, where the data are put faster when OE arrive, and OE is turned to 1, output enable is turned to 1. So this is a bit on the chip architecture of EEPROM. Next, we're going to look at RAM. Okay, RAM. What is RAM? So RAM, a bit different from ROM. RAM is what we call as a random access memory. Okay, so random access memory is different from ROM. It is a volatile type of memory, meaning that the data stored in RAM will always stay there as long as power supply is still on. It is used to store temporary data, and like ROM memory, there are many types of ROM which are available in the market. So what are the types of RAM that is available in the market? First, we have what we call as a static RAM. Okay, this is easy to fabricate. We use 4 transistors to store 1 bit, and it's very fast, suitable for system with small memory. And we have DRAM, dynamic RAM. Again, it is still easy to fabricate, only uses 1 transistor to store 1 bit, and it's used for memory of PC. And then we have EDO RAM, we have BDO RAM, we have SD RAM, and the latest technology we have what we call as a DDR RAM. Okay, the double data rate synchronous DRAM. So again, all of this E to E can be considered as old type of memory system, whereas nowadays, if you see in most computer system, including the latest microprocessor, very often you can see that most of the system uses DDR RAM. Okay, also the one that I've shown here, DDR RAM, this also can be considered old, because DDR RAM nowadays there's a lot of type of DDR RAM. Okay, we have DDR1, DDR2, DDR3. Now the most recent I can say it is DDR5 RAM. which is the fastest in the market. So how does a typical DRAM chips looks like? What is the architecture of typical DRAM chips looks like? So this is a typical DRAM chip. Okay. Let me pause. So again, we continue. Sorry for the bit of the intermission just now. So this is a typical architecture of your RAM chip. Okay. Similar to your ROM chip, we have what we call as a address bus here, and then we have your data bus again. This is connected to your 68K microprocessor. Okay, and then we have all of this pin here. So the main difference between your ROM and your RAM is this part here, write enable pin. Okay, so again, the output enable pin, we have the output enable pin, and we have the chip select pin, and lastly we have this write enable pin. So depending on the state of these three pins here, okay, we have a truth table that denotes the mode of the memory. Again, for example, if it's in 000 mode, okay, this can be described, so this refer to datasheets. So neglect this part over here, because depending on type of chip, this 000 will be different. You have to refer to the datasheet, but I can say is if it's in 001, you are putting the chip in a read cycle where the data is being put to the bus, and then if it's in 010, you are putting the chip in a write cycle in which the data is in a latch, and at 011 you are putting the memory in a standby cycle. This is for fast operation. When zero output enable is put to 1, the data inside this memory will be immediately put on the data bus. Okay, so that is on the RAM part, the architecture of your RAM. Next, we're going to look at what is an address decoder and why do we need an address decoder. For a memory system, okay, for a memory system and for the peripheral that to be connected to your microprocessor, all of this is connected to the same address and data bus. Okay, so example on the figure given here, you can see that you have your 68K microprocessor over here, and then you have all of these peripherals and memory chip. We have your RAM, and then we have your switch, the LED, and ROM. So this is all of the peripheral and devices that is connected to your microprocessor. Okay, so all of this is connected via the same address and data bus. However, you have to remember that at a particular time, only one device can be communicating with the 68K. So how do we do that? Okay, how do we specify that what and which devices is talking to the microprocessor? So this is where this address decoder comes in. So this is the task of an address decoder. So basically an address decoder, what it does, it will, based on the addressing that is being put on the address bus by 68K, it will decode which device is needed to be connected to the 68K. So if you look at back on your memory system, you have this chip select pin. So this chip select pin is the one that is connected to your decoder, address decoder. Okay, so whenever this chip select pin is being put to 0, okay, this is, though this is a bit counterintuitive, okay, but you select the pin by putting it to 0. You can see whenever this is 0, okay, on the truth table here, there is a mode that is being activated. So that's how you select, that's how the decoder, address decoder select which peripheral is needed to be talking to your 68K. So for example, if the RAM is being put to 0, so the chip select pin here will be put to 0. All of the other pin will be put to 1. Okay, all of the other chip select pin on other device will be put to 1. So during this particular time, we know that the RAM is currently talking to your 68K microprocessor. So that is the task of the address decoder. Okay, so how does it function? Again, the decoder will wait for a specific patterns or polar that's going to be sent by the 68K via this address bus. So it will constantly monitor the state of the address bus. Okay, if a certain condition exists, so what it'll do, it will send this SEL pin. So this, you can imagine that this decoder address and has an output pin SEL here, which is a short form for select, to 0. Okay, so remember again, when we put to 0, will be put to 0 to activate which device is currently talking to the 68K. So if this is put to 0 in this example, if you see, if this is put to 0, meaning that the EEPROM or RAM, this one will listen to the address bus over here. Okay, so it's like that. So this is the timing diagram that you can see. How does it behave? So whenever your SEL is put to low, whenever your SEL is put to low, whenever your AS is put to low and the SEL will be put to low, the addresses that is available in this address bus will be read by your EEPROM. So SEL will activate the pin CS, chip select, and cause selected memory device to be chosen. So this is how the address decoder function. Okay, there's two types of full address decoder. The first one is the full address decoder. In our full address decoder scheme, all addresses line must be used to access each physical memory location, either to access data or activate selected device. Whereas in a partial address decoder, not all of the address line is available for address decoding. This method is compared to the full address decoder scheme is a bit simpler and less expensive, and we can use a decoder chip for this purpose, be it a 7LS138 or the 7LS139. So this is the difference between full address decoder and partial address decoder. So you will look at in detail what's the difference. So this is just to explain to you now that for full address decoder, you will use all of the address line to address the selection of the peripheral device to be connected to your 68K, whereas in a partial address you don't need to use all of the address line. Just a few address is enough for you to select which type of devices needed to be connected to your 68K microprocessor. Okay, so now we're going to look at on how to design the decoder system in order for you to interface it with your 68K. Okay, so how are you going to design this? Okay, there are a few steps that you need to remember. First steps is for you need to determine the base address that you want the decoder to be accessing, that you want your 68K to be accessing your peripheral. Okay, so and then you need to specify the size of the address that you want to allocate, and lastly the N address, which can be calculated based on the base address and the size of the memory. Okay, the size of the memory minus by 1. So that's how you figure out your N address. So basically what you do in the first step A here, so imagine that in your 68K memory system you have this memory range from so your address bus is 24 bits, meaning that you have 00000 up to FFFF. Okay, so in the first step you need to identify how many address that you're going to use in order for you to interface this in order for you to interface this with the memory module. So the size of the what we call this, the region, your address region, will be depending on the size of memory module that you want to use. So meaning that if you want to connect your, for example, 64 kilobyte memory to your 68K, then there's a size that you need to calculate on this address bus here that you're going to use. Okay, so this is the what we call the region, the address region that you're going to interface with your memory or something, be it your EEPROM or your RAM. Okay, so here you have your base address. So this is the base address. So this is the base address, base address, and then this is the size. Okay, this is the size, and lastly here is your N address. So here is your N address. Okay, so again you need to minus by 1 because this is you're starting from 0, right? So you need to minus by 1 to get the N address. Okay, so whenever you want to design, you always need to start with this, determining the address range for each of the component that is connected to your 68K. And then next, the second step, what you need to do is you need to determine all of the address line that will be linked to memory and the decoder. Okay, you need to find the total address line that is directly connected from the microprocessor to memory. Okay, the line that is directly connected to the microprocessor and memory is via the address bus. So remember, this is via the address bus. Okay, and then you need to find the lower address line that is connected to the memory. Okay, this is next you're going to see this is the UDS and LDS part. Okay, upper data stroke and lower data stroke, because later on, if you can remember correctly, and later on we'll see, your address consists of an odd region and even region. Okay, so depending on the lower address, which is A0, okay, we'll specify whether to write it on the odd side or the even side. Okay, and lastly, the balance of address line is connected to decoder. So the balance of this address line from these two, from the first one that you have determined, the total address and the lower address, the balance of it is the one that is going to be connected to the decoder. Okay, so let's look at in detail how we're going to do this. Okay, so let's say, so this is an example. Let's say you are building a system. You need to design a system, microprocessor system, that have 64 kilowatt of RAM, okay, or 128 kilobyte of RAM that is needed to be interfaced with 68K, and then you have specified that the base address that you need to connect this RAM with the 68K starts at 480000. Okay, so the first thing you need to do, again, the steps here. First, you determine what is the base address. So the base address is at 48000. So means that you have specified in your memory address system, starting at 48000 here, 48000 here is the starting point of the address, the memory address that is being connected to the RAM. Okay, so you need to imagine again, you have your 68K, this, and then you have your RAM over here. This is your RAM. All of this address bus, is going to be connected to the from the 68K to the RAM. Okay, so this is the address bus. So this is address bus. Okay, so and then you need to identify, once you identify the 48 the base address, you need to identify the size of the memory. So the size of memory here is 128 kilobyte. So 128 kilobyte here. Okay, so based on the starting address and the size of the memory, you can calculate the end address of the address memory. Okay, the end address of the address memory. So this part here. So how are you going to calculate that? Very simple, as mentioned in the previous step. Is the base address plus the size of the memory. Okay, the size of the memory minus by 1. So in this case, our base address is 48000 plus 128 kilobyte. Converted in hex minus 1, we will get 49FFFF. So in order for you to see clearly on this, okay, let's look at the sorry for this instance. Okay, let's look at how we're going to calculate this. Okay, here, so I already did this, pardon me. So go to mode and then go to base N. I think this is already covered by Dr. Zamani, so I just a refreshment for you here. Okay, just to refresh things up. Okay, you have your base address at 48000000. Okay, and then the size of your memory that you are going to connect to your 68K is 128 kilobyte, means that is 128 times 1024. 1 byte is 1024 bit. So remember, yeah. Sorry. So one byte is 1024. So you have one kilobyte is 1024. So remember, we are multiplying 128 with 1 kilobyte. So you have to multiply it with 1024. So I think this already been covered by Dr. Zamani. And then finally you minus this by 1. So what do you get? Sorry, pardon me, I think I made a mistake here. Again, so when you put 480000 hex as a hexadecimal number, then plus with 128 multiply with 1024, and this is must be okay. Finally you minus this by 1. So this in hex, so you get 49FFFF. So that's how you calculate the end address. So means that all of this region in your memory, in your addressing memory, 48000 to 49FFFF is being allocated by your 68K to be connected to the RAM. Okay, so that's how you allocate memory for your peripheral. Okay, the next step will be for you. So let's look at what is the next step. For you, the next step will be for you to find the total address line that's directly connected from the microprocessor to the memory. And you need to figure out the lower address line that is connected to the memory, and lastly the balance of address line that is connected to the decoder. So this is how you're going to do, how you're going to perform steps B, step B. So you need to come up with this kind of table. Okay, first let's look at the address range here. So first you need to, I'm sorry, a bit clumsy over here. You need to come up with this address range that you determine in step A. So this 48000. So you draw a table, okay, consists of this kind of table. Okay, the most left column is the device, and then in the middle column here is the address line, and then the last one is the address range. So first you determine this address range. So the base address range is the starting address range that is being given by the question, 48000. So after you have figured out, after you have put the base address here, you're going to draw what is the value on each of this address line. So remember, the middle part column here, is your address line. In your 68K microprocessor, you have 24 address lines, so 24 bit, starting from 0 up to 23. So you have already figured out that your base address is 480000. So means that if you can see here, the first character denoted by 4, the first number denoted by 4 is this part. Okay, so 0010 is 4. Okay, and then from address line 16 to 19 is 8. Okay, so this is 8. Okay, and then all of the other is 0, 0, 0, 0. So in each of the address line in this row here, you need to put the binary value of this base address. Okay, 4, so it's 0, 1, 0, 0. 8 is 1, 0, 0, 0. 0 is 0, and such and such. And then next you need to put in the N address on the second row. So I change the color, maybe I can change this to red. Okay, this to red. So in the second part, you need to put the N address in a binary number. Okay, in the second row here, okay, second row here, put the binary or the bits for the N address. So here start with 4, again 4 here is 0, 1, 0, 0, so the N address, and then 9, so 9 is 1, 0, 0, 1. Okay, this is 9, 1, 0, 0, 1, and then F is everything is 1. So you can see here, this part here, this 1, 1, 1, 1 will equal to F. So again, similarly, this 1, 1, 1, 1 will equal to F, and all others are F. So you need to put in all of this value. Okay, again, you need to construct this table whenever you are designing the address decoder, or you are figuring out how you're going to connect your peripheral to your 68K. So if there is this kind of question, I'll sure there'll be this kind of question in your final exam. Remember to construct this kind of table. Okay, and then lastly, you need to figure out, okay, once you have figured, you're filling all of this value in binary for the base and the N address, this now comes the part that you're going to denote which address is going to go to the address bus and which address are going to put in the decoder. Okay, you're going to be connected to the decoder. So you're going to you can imagine that from the A0 to A whatever, okay, A23 24 bit, yeah, some will be connected to the address bus, okay, which directly goes to your RAM. So you have your RAM every day, so pardon me because I'm not good at drawing. So let me put this color. Okay, okay, sorry. Okay, some will be put at will be connected to the address bus and is directly connected to your RAM. Okay, the remaining of your address pin, okay, let's put this in green, okay, will be connected to your decoder. Okay. So this blue part here will be connected to your memory, your RAM or your ROM, and this green part here will be connected to your decoder. Okay, decoder. Okay. So you got to remember this. So how do you determine which part of your address pin that is connected to your RAM and which part is going to be connected to your decoder? So now you need to figure that out. Okay, let me erase this first. So the way we figure that out is first you need to determine on your address bus which pin changes. For example, if you can see over here, starting from 0 to 16, let me use green color for this. Okay, from 0 to 16, okay, all of this part here changes its value from 0 to 1. So all of the bit that change, you denote it by X. Okay, you will fill this row over here with X, meaning that all of the pins, all the address pins that changes, this will be connected directly to your RAM or to your RAM module, or sorry, to your ROM module, to your memory module. Okay, so all of the pin that changes, you will denote it by X. Okay, so we have over here A0 to A16 that changes. So first we will denote all of this by X, and then the remainder pin that doesn't change, if you can see here, this yellow part here doesn't change the value from 00, 00, 11, 00, 00, 11. So this will be connected to your decoder part, or to your decoder device. Okay, this will be connected to the decoder device. So this part over here will be connected to the memory, and this part over here is connected to your decoder device. So that's how you figure out which part of the address pin is connected to the memory and the part that is connected to the decoder. Okay, so this is just an explanation. Start from the right again. Bit that start with 0 and end with 1 directly go to memories, meaning that bit that change go directly to memory. So in this example, A0 to 16 go to your memory, but again, remember I mentioned to you just now, A0 is connected to UDS and LDS. Okay, this is connected to UDS and LDS, meaning that A0 connected to UDS and LDS. So A1 to A16 here is connected to the memory. Okay, and the remainder A17 to A23 will be connected to your decoder. So that's how you figure out which pin, which address line or address bit that you need to connect to your directly to the peripheral or your RAM or ROM, and which part can be connected to your decoder. Okay, so the last step for you is to design the decoder circuit. So generally the easiest way is for you to use a NAND gate for this. Okay, so if you remember NAND gate, okay, NAND gate looks like this. Okay, you have, this is just a simplification for you, X1 and X2. Okay, the NAND gate, whenever the output, whenever the input is 0, okay, whenever the output is 0, whenever your input, both of the input are 0, your output will be 0. Okay, your output will be 1, sorry, your output will be 1. Okay, let me check again. NAND gate, sorry, I also forgot what NAND gate. Truth table. So yeah, I'm correct. Okay, so whenever both of the input is 0, the output will be 1. So according to this according to this output. Yeah, okay. Sorry, I got it reversed. Whenever the input is high 1, your output will be 0. I got it reversed, so you can, here is easier. So this is your NAND gate. So whenever the input of the input is high, the output is 0. The condition for it to be 0, okay, the condition for it to be 0 depends on both of the pin to be, or all of the pin to be 1. So that is the important thing you need to remember about NAND gate. Okay, so remember, why do we need 0? You might ask yourself, why do we need 0 over here? Again, as I mentioned earlier, chip select part over here depend for it to be 0 in order for you to make the chip function. Okay, you need to put the chip select to 0 in order for the memory to be function. So the output of your full address decoder over here, okay, you can imagine this will be connected to your RAM. So this pin is going to be at chip select. So you need to be 0. You need to be 0 to activate the RAM chip. Okay, you need to be 0 for you to activate the RAM chip. So how do we make a full address decoder? Again, we can use the remaining unused address to select the RAM over here. So the most easiest way is for you to use a NAND gate. Okay, so how do you design a full address decoder using a NAND gate? First, you need to identify the remainder, the address bit that you have figured out just now, which part is going to be connected to your address decoder. So we have A17 to A23, A17 to A23. So we have A17 to A23, okay, A17 to A23, which is denoted by this bit. So 00 00 10010. So 00 10010 1. So pardon me, 00 10010. Okay, so starting from A17, yeah, A17, all of the pin that have 0, you need to put the input as bar over here. Okay, so 0 0. So A17, this is, let me draw it clearly for you. Okay, so we have A17, A18, A19, A20, A21, A22, and lastly A23. So this is 0 0 1 0 0 1 0. So if you can see here, the input towards this NAND gate, all of the part that denoted by 0 is a input with a bar. Why a bar? Because 0. So 18, A18 here is also, you put it input with a bar. All the pin with 1 is just a pin directly connected to the NAND gate, and you can imagine such and such. So this is how you design your full address decoder. Why is it called full address decoder? Because you are using all of this address to decode to decode which chip you need to select. That is why it is called full address decoder. One last thing that I need to highlight is this AS pin over here. The AS pin over here is always like this, yeah. If you can see, AS stands for address group, if I'm not mistaken. AS here, okay. So when AS is 0, so AS need to be 0 in order for select to be 0. So that's why the input to AS here is 0. Okay, so you can imagine it. So whenever you looking back at the truth table just now, for this to be 0, for the output of the NAND gate to be 0, all of the input needed to be 1. So you can imagine that whenever this condition happens, whenever this condition is detected on the address bus, all of the output on this pin will be 1. Okay, all of the output on this pin will be 1, causing the select to be 0, causing the RAM that is connected to the address decoder to be selected. So this is how you design your full address decoder. So again, I repeat the steps for you. First, determine the base address, the size, and the end address. Okay, how you determine it is based on this equation over here. Identify the base address that you want your peripheral to be connected to your 68K. Then what's the size of the addressing memory, and then find out what's the end address, and based on that, figure out which part that is connected directly to the address bus and which part is going to be connected to your decoder. Okay, so based on that, finally you design your full address decoder of your system. So that is how you design your full address decoder. So I think I'll stop from here. So we will continue with the partial address decoding scheme in the next lecture. So until then, thank you everyone and have a good day.